Okay, so as I was saying, there's a lot of things that cancel. And so when we finally write this out, what we end up with is we get 6 over 8 u naught over h squared. Okay? And so let's plug in, for example, so we'll check when the displacement u naught over h is equal to 1/2. So basically what we're saying is the displacement amplitude is equal to 1/2 of the beam width. Okay, so then what we get is we get that the f cubic over f linear is 6/8 over 1/2 squared, and that evaluates to, I have to use a calculator for this, 18.8%. Okay, so the first thing I want you to notice from this is that the nonlinearity, basically the way we should think about the displacement amplitude, is it's the amplitude relative to the width of the beam. Okay, so beams that are narrower can go to smaller displacements before they start to become nonlinear. And what we see is that the nonlinear, the force from the nonlinear spring term is about 20% of the linear force, so fairly significant when the displacement is half of the beam width. Okay, and so that was in the lecture that I had about the different kinds of flexure designs. We saw that it was sort of the flexures went nonlinear when the displacement amplitude was somewhere between 1/4 to 1/2 of the beam width. So if we have a beam that's 1 micron wide, right, we can only displace about 250 nanometers to maybe half a micron and use that small linearized approximation. Whereas if we have a beam that is thicker, right, if we quadruple the beam thickness, then we quadruple the amplitude that we can operate at. And this is just true in general. So the next thing that we want to deal with is how do we handle residual stress, okay? And so residual stress, sigma naught, you remember there was Stoney's equation, so if we deposit a film, let's say it's polysilicon or whatever our material is, it has some residual stress in it. So we would like to calculate how that affects the spring constant. And if you remember strain energy in general, the way we got the strain energy is it's the integral of it's the stress integrated over the strain, like this. And what we saw before, we had W is equal to then the integral of E times epsilon d epsilon. Okay, so now what we're going to do is we want to calculate the I need to be a little bit careful here, because if you remember that this is the energy density, so I'll call it basically dW. Okay, so this is the strain energy density. Okay, now what we want to do is for a constant residual stress, we find that dW is going to be equal to the integral of sigma naught d sigma, and so what we get is it's basically sigma naught times sigma naught d epsilon, so we get sigma naught times epsilon. And so what we need to do is we need to find the total strain energy. Then it's the integral of over the volume of the strain energy density. Okay, and so what we end up with is it ends up being the integral over the volume of sigma naught times epsilon d volume. Okay. Now, what stress do we use? Well, let's go back to our bending beam here, and somewhere in here. Well, the total stress is equal to the axial stress plus the bending stress. But when we integrate over the volume, if we want to calculate the product, sigma naught is some constant. Let's say it's tensile stress in the beam. So if we look at the bending stress, if you remember, like if we look as we cut the beam like this, so this is over the height, bending stress looks like this. Whoops, sorry, it should go straight through 0. So it's symmetric, right? It's basically positive at the top and it's negative at the bottom. So the product, so this is EB as a function of y here. So the product of sigma naught EB as we integrate from minus h over 2 to h over 2 dy is equal to 0, right? Because this is symmetric. When we do the integral and when we integrate here, so this gives us 1/2 e times epsilon squared. This integral is epsilon squared, and so it integrates to a non-zero value. But in here what we're doing is we're integrating the product of a constant times this distribution over the volume, and so this integrates to 0. And so as a result, the part of the strain energy due to sigma naught, due to residual stress, that's what I'm going to call this, is just going to end up being the integral over the volume of sigma naught times epsilon sub a dv. Okay? So epsilon a was the axial stretching part of the sorry, not epsilon sub a, it's epsilon sub x. So epsilon sub x of x is 1/2 d squared u dx squared. Okay? So the bending part is equal to 0, and all we have to do is evaluate the product of sigma naught times this guy. And fortunately, again, I did that in MathCAD, right? We already evaluated the integral, we already integrated epsilon x over the length, right? So epsilon x is 1/2 du dx quantity squared. And we already integrated that over the length of the beam, and this is what we ended up with, pi squared u naught squared over 4l squared. So, sorry, this is not. Okay, so let's write this out. Here's what we're doing. We've got the strain energy due to residual stress is going to be the integral from minus L over 2 to L over 2 times the integral from minus h over 2 to h over 2 of sigma naught times 1/2 du dx squared dy dx, and I need to multiply by b, right? So that's the last part of my volume integral, is integrating over z, and nothing changes over z, and so I just multiply by the beam width here. Actually, all this stuff is constant over y also, and so what I end up with is that this is equal to b times h times 1 integral from minus L over 2 to L over 2 of sigma naught times 1/2 du dx squared dx, and this is what I said I had already evaluated, so when we multiply this all out, we get sigma naught bh over 2 times pi squared u naught squared over 2l. Okay, so this is basically C MathCAD. Okay, so this is the additional strain energy term that we get in addition to what we had before. Okay, so W total is now going to be equal to the W from the previous calculation. So we'll say basically like this is axial plus bending plus W due to residual stress. Okay. And so if I write all that out, I guess I can make this a little bit bigger. So I could write all that out. I got EB times H pi to the 4th times 8 H squared plus 3 U naught squared times U naught squared over 96 L cubed plus sigma naught B H pi squared over 4L and the U naught squared here. Okay, and so this is the U naught squared. So this part here is this, and so this is what we had before. So that's the residual stress term. And so now what we're going to do is we have the same sort of energy function. So we're going to calculate du naught, which is du naught of W total, minus F times U naught. And when we calculate that, what we get is F is equal to pi to the 4th over 6 E B H cubed over L cubed times U naught plus pi squared over 2 sigma naught B H over L times U naught plus pi to the 4th over 8 E B H over L cubed times U naught cubed. Okay, and so what do we got? This is the linear term. This is the part due to residual stress. And this is the large amplitude term. Due to axial stretching. So now neglecting this large amplitude term, we can see that basically what we're going to end up with is the linear spring constant consists of the geometric part and the part due to residual stress. So we'll say at small amplitudes. The spring constant is going to be K equals pi to the 4th over 6 EB H cubed over L cubed plus pi squared over 2 BH over L times sigma naught. Right, because then both of these things multiply U naught, so they're like a linear spring term. So this is geometric. And then there's a part that's due to residual stress. And just like we did before, let's compare the ratio of those two things. So K sigma naught divided by K geometric. That's pi squared over 2 BH over L sigma naught over pi to the 4th over 6 EBH cubed over L cubed. And so we get 6 halves times 1 over pi squared, and more or less this right 3 over pi squared is just about equal to 3, so I'm going to just sort of simplify things. We get L squared over H squared sigma naught over E.